Okay, in this video, we're going to talk about concentrations and how do we create the right concentration solution. So to do that, we first have to remember our math, okay? So to be able to find the concentration of a solution or to have the proper concentration of the solution, we usually want to solve using molarity. That's the most common way that concentration is done in chemistry. So if you recall that molarity is moles of solute divided by liters of solution. It's important for us to remember that it's liters of solution and not liters of solvent. So if you're looking at your notes, you might want to highlight that. It's the total volume of solution here, not just the solvent, if we do it properly. Okay? Now, we can't really measure moles in lab, so we usually use this in grams and then convert. Okay? So let's talk about that. Just a reminder, a little bit more practice of our math. So if we're looking at a problem like this, what is the molarity of a potassium chloride solution that has 85 grams of it put in with a volume of 400 milliliters, okay? So let's find that concentration. So obviously, if we have grams of potassium chloride, we can find the moles of potassium chloride, okay? If our volume is 400 milliliters, we want to convert this to liters, so it'd be 0.4 liters, all right? So looking at our math, it'd be pretty straightforward. It should be pretty easy for us at this point in the year to take the 85 grams, use the molar mass of grams per mole, and we have 1.14 moles of potassium chloride. Obviously, we convert to 0.4 liters, and the molarity is a 1.14 moles of potassium chloride divided by the volume. So we end up getting 2.85 moles per liter in this, capital M or moles per liter as our answer, okay? So just a reminder of how we would get from mass and milliliters to moles per liter in our math, okay? It's probably more common actually that we do a practice or we have math like this practice problem. So in this case, we want to make 100 milliliters of a 0.25 molar solution of magnesium nitrate, okay? So if you go into lab and you want to create a solution at a very specific concentration and you want a specific amount of that, this is what we're looking at for this type of practice. We want 100 milliliters and we want it to be this concentrated, okay? So the question is how many grams of magnesium nitrate should we use, right? So we're going to have a solid magnesium nitrate. We got to figure out what mass of that are we going to pour into the water to get 100 milliliters. So again, okay, we want to convert that 100 milliliters to liters, so it's only 0.1 liters. We know that 0.25 molar means 0.25 moles per liter. We know our equation for molarity is moles per liter, or you could rearrange it and say that the molarity times the liters equals your moles, okay? So if you have 0.25 moles per liter and you have 1 liter of it, you're going to need 0.025 moles of your solution, okay? This also could be done as a long stoichiometry problem if you wanted to. You could do this step in combination down here, just using your molarity in the math, okay? So you have 0.025 moles and you use your molar mass to find 3.71 grams of that, okay? Later on in the video, we'll actually show you the way to combine these two into making one kind of stoichiometry problem, which you might even be more comfortable with doing, all right? So now we know if I want to make 100 milliliters of this solution, I want to use 3.71 grams of the powder, and I'm going to dissolve it in enough water to give me a total volume of 100 milliliters, okay? Usually in a lab setting, if you use 100 milliliters of water and pour this much mass in, you will get very, very close to the right concentration. The problem is that the actual volume of water is not going to be the same as the volume of your solution, okay? What I mean by that is if you use 100 milliliters of solvent and 3.71 grams of magnesium nitrate, these 3.71 grams do take up a small amount of volume. So if you're using 100 milliliters of solvent and you're using 3 grams of magnesium nitrate, when you're done mixing them together, you'll have a little bit more than 100 milliliters, which means your concentration will be a little bit smaller than 0.25. Now, normally in a typical lab setting, that will be negligible, okay? Especially if you're talking about concentrations less than 1 molar, because there just isn't enough volume here to make a difference. If we want to make the solution perfect, and we want to make sure that there isn't any little discrepancy in that, the way we do that is through a technique called volumetric preparation or a volumetric procedure, okay? So the steps are very similar to what you would normally do, except for you just account for the fact that you're going to have that volume change when you dissolve your solute, okay? So first thing we do, calculate the needed mass of solute, which we've already done. Mass out the proper grams of the solute based on your calculations, so get the right grams. We want to fill that volumetric flask about 2/3, half, partially full of solvent, okay? Not completely full. Then we want to add our solid solute. Okay, so you put the solute with the solvent, but you're not at the number of milliliters total yet. Okay, completely dissolve it. Step 5 is by far the most important step in this process because the dissolving process is where the volume changes. Okay, so you have to dissolve the solute before you get to your final volume. And once you get to the solute all dissolved, then you can finish adding solvent until you hit the exact volume you need. Okay, now this can be done in any kind of flask, but volumetric flasks are unique to this because they come in several sizes, but each flask only measures one volume. So here we have a 2,000 milliliters, here's a 500, a 200, a 100, a 50, a 25. So we could use this flask if we wanted 2 liters. We could use this flask if we wanted a half a liter. We could use this flask if we wanted 200 milliliters, okay? So the downside to this is you need to have a lot of equipment for different amounts, okay? A typical Erlenmeyer flask has lines in lots of places. They're not as precise, but you could use this technique using one of those flasks too if you needed to, okay? Now, we're gonna go to a little video of it actually happening because it makes more sense once you see the actual process. In this video, we are going to be making up a solution, and our goal here is to make 0.20 molar copper sulfate solution, and we want to do that volumetrically. Okay, so to do that, we of course need to have our copper sulfate solid first. We're going to need to have distilled water to do that, and we're going to need to have a volumetric flask. So we want to make 500 milliliters of this, so we're going to use a 500 milliliter flask because volumetric flasks only have a single line on them. You can see it like right here. So they only can measure one volume as we do this. So step 1 is our math, okay? So to get 500 milliliters of 0.2 molar copper sulfate, we're gonna have to start with that half a liter and then use the molarity of the 0.2 moles per liter and then use the molar mass of the copper sulfate. And that gives us an answer of 24.97 grams of copper sulfate. Now, here's what we need to trust the math because when we mix this all together, we just have to trust that we did the math correct, so we will end up with that 0.20 molar solution. Okay, so step 1 is to go to our balance and get the 24.97 grams of copper sulfate, which I have already done. That's sitting there ready to go. Step 2 is to start mixing it into our volumetric flask to get this proper. Now, you can do it one or two ways. You can add a little bit of water first. That is kind of a standard way of doing it. But you can also start with the solid if you prefer. So I'm going to start with the solid because I don't like it when the solid touches like a wet neck of a flask, and that actually causes it to stick. I just don't enjoy that. So I'm just going to dump that in using my funnel, and now we have our copper sulfate at the bottom there. Now, that solid takes up space, so we need to account for that. But it takes up a different amount of space than when we dissolve it. So this is why we need to use a volumetric procedure, is because the space a solid takes up is not the same as the space it takes up once it's actually been dissolved and the ions break apart and it intermixes with the solution. There's actually a difference there, okay? So we're gonna start with our distilled water, and I'm gonna start by just pouring a decent amount of distilled water in. I'm not going to fill the flask completely full at start because I want to dissolve that copper sulfate first. I am going to fill it full enough where I have enough volume here so I am going to be able to get that to all dissolve, okay? So by doing that, here's my solid. I had to dissolve this first. So I'm just going to swirl it. And with swirling, I should be able to get this to dissolve, okay? It may take a little bit to do that, so we're going to swirl this together. And we'll continue to swirl until all of that copper sulfate on the bottom is dissolved into this liquid, okay? Okay, so now if we take a look and see, I obviously stopped the film and started another segment here. The solution is much darker. And if we look, we can't see any crystals on the bottom anymore of the flask. So even as I swirl it, there's nothing, I can't see any of the solid. So that's how you know you've dissolved it all, is because you have all the solid particles are gone. And obviously your solution will get darker and darker as that happens, all right? Now, last step as well, I have most of the water in, but I need to fill it up to that line right here with my pinky finger is kind of showing. So we're gonna set that down, and I'm just gonna use, again, I'm gonna start with my funnel. I'm gonna pour a little bit of salt water and distilled water in. I'm gonna pour until I get close. And then when I get close, the last step is to use a squirt bottle, something that is much more precise, and then just squirt water in until you get to that line exactly. So you notice I'm going nice and slow, making sure I don't go past that line, because it really isn't a perfect way to fix it if you go past the line. And there I am. So you see how now the end of the water matches that line exactly, okay? So now I have created my solution. Now, last but not least, we do want to give it one more quick swirl, so that way all of the stuff in the neck gets mixed in with the stuff in the box. And then, because I don't want to store it and keep it in this, I'm going to put it back in my stock bottle, which also will do some final mixing for me. So we'll just pour that in. And I have just created, to the best accuracy and precision I can, 0.20 molar cover sulfate solution.